Hello and welcome to Mechanical Y. Here I have a six-sided die. Each side is labeled with an integer between 1 and 6. If I were to roll this die and then ask you what the likely outcomes would be, you would quickly point out that there's an equal chance of each one of these integers landing face up. Now let's throw a wrinkle into this experiment. Let's say I roll this die twice and then sum the results of each of the two rolls. I ask you again, what are the likely outcomes? First, you'd point out that the possible outcome will be a sum between 2 and 12. Second of all, you'll point out that there are 36 possible ways to reach one of these sums. And it's pretty easy to map out all of these possibilities. But you may also point out that since there's 11 possible sums and 36 ways to get there, certain outcomes are more likely than others. This is true as there are 6 different ways to reach a sum of 7, but only one way to reach a sum of 2 or 12. And it can be clearly seen that there is a distribution of possible sums. But let's make this even more complex. Let's say I roll this die 87 times and then sum the results of each of the rolls. What are the possible outcomes? First of all, we know that the sum will be an integer between 87 and 522. Second of all, there are 50,000 trillion ways to get to one of these sums. What are the possible outcomes? You can forget about mapping out all the possibilities as we did with the 2-die roll experiment, but using some intuition and some past experience, we may be able to point out that a sum of 304 or 305 are the two most likely results. However, a more detailed description of the exact outcomes is going to require much more detailed mathematical analysis. For instance, what is the probability of a result of 428 coming up? Not so easy. But now let's make this even more complex. Let's sum the result of 87 die rolls, but mix up multiple dice with different number of sides. Now we have lost all of our ability to use intuition and experience. Intense mathematical analysis is required to get the behavior of this system. Unless, that is, we just start rolling these dice and then tabulating the results. And after rolling and tabulating many times, we can plot these results on a graph. Eventually, we're able to see a pattern. And we can look at this pattern to get insight into the system and what the likely sums are likely going to be. If we do this, we're using something called a Monte Carlo method. While there is no strict definition of what it can be called a Monte Carlo method, the term is generally applied to any approach or method that is used to determine the behavior of a system through random sampling of variables. Each variable typically has a range of possible values, and we typically know or can find out this range and the probability of a value of being within this range. In the case of this die rolling experiment, the system is these dice. The system's behavior is the sum that we're looking for, and each die represents an individual variable. The act of rolling each die is the random sampling of each of those variables. Let's look at a simpler die rolling experiment. Let's say we just take these 6 dice with sides 4, 6, 8, 10, 12, and 20. Let's roll them each once and sum the results. We know that the sum will be an integer between 6 and 60. And there are 460,800 ways to get to one of these sums. We can start rolling and tabulating the results to figure out the behavior, effectively performing a Monte Carlo process, but there's a catch with Monte Carlo methods. The catch is that there must be many random samplings to determine a system's behavior. How many? On the order of tens of thousands, hundreds of thousands, or even millions of samples if possible. Now it seems like we've solved one problem with another. I can't map out almost 500,000 possibilities, and I can't roll these dice tens of thousands of times or more. But what I can do is run a computer simulation. You see, I know the probable result of each individual die roll, and I could quickly program this into computer software like Microsoft Excel, and after only a few minutes, I can have the results of 25,000 simulated die rolls. I figure out the likelihood of getting a particular sum, and I can plot those percentages on a convenient graph. As with a 2-die roll experiment, we see that there is a distribution of possibilities with certain sums being more likely than others. I find that I'm likely going to get an average sum of 33. Furthermore, I know that only 10% of the rolls will be above a 43, while only 10% will be below a 23. I can further use this graph to help predict other likely outcomes of rolling these particular dice. But because I've only sampled up to 25,000 different data points out of almost 500,000 possibilities, it would be wise to repeat this experiment several more times to make sure I didn't randomly sample some extreme unique case, just by chance. So are Monte Carlo methods useful? Are the results reliable and descriptive? Yes, these methods can be used a number of different ways, including in optimization, determining outcome probabilities, numerical integration, modeling the behavior of fluids, or even just getting a simple feel for a system. You can even approximate the value of pi using a Monte Carlo simulation. First, you take a unit square, then randomly sample points inside that square. Then determine the percentage of these points that lie within a unit radius arc from one corner. Since the arc represents 1/4 of the area of a circle, the resulting probability that a random point is within the arc should be 1/4 of pi times the radius squared divided by the total area of that square. The square is a unit square and the radius is a unit radius, so this probability simplifies to 1/4 of pi. I personally ran the simulation with 25,000 random points, and I came up with a value of pi of 3.14016, which is pretty close to the actual 3.14159 continuing. Monte Carlo methods are also useful when the system is far too complex to represent precisely with a chart or mathematical equation, especially when variables depend on each other. For a real-world example, let's look at a factory setup and the individual machines in it. Let's say that I'm setting up a new production line by rearranging my machines. And what I want to do is estimate the power consumption before I actually turn them on. But there are many machines, and each consuming different amounts of power at different times. It's hard to come up with and solve a precise mathematical equation that represents a factory. So instead, I can sample the power consumed by each machine before I set up the production line and use a Monte Carlo process to determine the likely power consumed in the new line. Or I can run a simulation given information about each machine that I would have gathered ahead of time. In the end, this process would look very similar to the dice rolling experiment. Historically, we have found that using Monte Carlo simulations to determine a system's behavior can be very accurate and insightful. However, as I mentioned earlier, the accuracy depends on the number of samples taken. Let's consider the example where I determine the value of pi. If I only sample 25 points in that unit square and not 25,000, I get a relatively inaccurate value for pi of 3.33. Furthermore, Monte Carlo methods are best when real systems are sampled and not simulated. Random sampling in computer simulations can only be as good as the random number generator used in the software, which historically has turned out to be quite good, but in some cases where the system is incredibly large or incredibly complex, computerized random number generators just don't cut it. Nevertheless, Monte Carlo methods and Monte Carlo simulations represent powerful tools that can be used to analyze very complex systems very quickly. Well, thank you for watching. I hope you found this interesting. If you did, please like and share this video, and please subscribe to stay up to date on new content. Also, please visit us at our website, www.mechanical-y.com.